Hello. In the year 2050, the world is projected to have 9 billion people. And at a meeting of the United Nations in 2009, it was stated that we actually need to double our current rate of food production if we're going to be able to feed the world's growing population. So, a group of folks at Microsoft Research started to think about that problem. How could we use technology to enable data-driven farming and to maximize yields for farmers? And so we explored a whole lot of ideas, and one of them is the idea of precision agriculture. So if you're not familiar with this idea, in the case of precision irrigation, the idea is instead of homogeneously watering an entire field, where every part of the field gets the same amount of water, you can give each part of the field only the water that it needs. So when you think about it, there's little dips and divots in a field, and so water may run down, and the bottom may get more than the slope. And then this can also be applied to many other things. Think of pesticides and applying fertilizer and things like that. So you can reduce costs by only using exactly what you need and no more. So this seems like fairly easy to implement, right? We have IoT, so we get some sensors and see what we can do with this. Now, when I started working on this project, I was speaking with our principal researcher, Ranveer Chandra, and he told me one of the first challenges is that it works out to roughly $1,000 a sensor to do this. Does that sound crazy to anyone else? Because that sounded crazy to me. I was like, no, let me show you this website. It's great. You can get sensors for like tens of dollars, not thousands of dollars. And of course, he was well aware of this. And it turns out the problem is not, of course, the sensor itself, but the infrastructure that is needed to support that. So my first thought was, OK, maybe it's power. We obviously don't have electrical outlets in the middle of a field in farmland. So perhaps it's the cost of that. And it turns out that that is a little bit, but that's not the majority of the cost. We actually use solar panels to provide power for the devices. And the solar panels run roughly $50 to $100 US per solar panel. So that wasn't the issue. If you take a look at our setup, we actually have, it shows our sensor board right there. You can see our sensor board, and it's enclosed in some waterproof casing with some of the leads for measurement coming out. And then the solar panel is on top, and it works even in gray Seattle, where we have one of our farms stood up. And then we also have a camera that's taking real-time imagery in both natural color as well as infrared to give that real-time insights into the farm. OK, so if it turns out it's not the solar panels, it's not the sensor itself, where is that $1,000 per sensor cost coming from? Turns out it is connectivity. It's getting data from the actual devices into the cloud where we can do something useful with it. Now, there's a couple different things that we can do. I'm actually going to come back to connectivity and how we can solve that better. But for now, let's assume that we just want to reduce the number of sensors since we have this $1,000 per sensor price tag on it currently. And so to reduce the number of sensors, there's something that we can do. And that is, if we have aerial imagery from overhead on the farm and we use a smaller number of sensors throughout, we can actually use machine learning to predict various sensor readings in areas where we don't have sensors. And so we looked at gathering aerial imagery. There's actually two different ways we've done it. We started with drones. And drones are a great use case for drones right there. They can fly overhead. There's a small screenshots there of an app that we made for the farmers. So the farmers didn't have to manually fly them. They could just set some points on an app, and then it would follow that path. Or they could specify an area, and the drone would do a sweep over that area. And we actually programmed in some cool stuff, too, around optimizing battery life to use the wind and such. So very, very cool stuff there. But there are some issues with drones. Their battery life, even the best drones, can fly for maybe 35 minutes. And you have a very big farm. That can be challenging. There is some cost to drones. They're going to be hundreds or thousands of dollars, but you just need one. And then the biggest thing is regulations, right? There's a lot of places where it's just very difficult to fly drones, and it does change in every country. And so we also have a different solution, And that's using helium balloons. So these are tethered helium balloons, large helium balloons, and we're using that in several areas as well. And you can see that's Ranveer actually launching one right now in that image, where it's a big helium balloon with a camera attached, and that can be staked into the ground, or it can be carried by someone to get a kind of a roving map of the farm as well. So whichever method we choose, you can gather aerial imagery in that way, and then couple that with the reading from the sensors that you do have. And then from that, we can build machine learning maps of the farm to measure the temperature, the moisture levels, the pH levels, all in areas where we don't have sensors as well. And we're doing this mixing kind of conceptually. Our model mixes two different things. One is the spatial smoothness, meaning that 2 points that are close together in the farm are going to have fairly similar values. So the temperature, is going to be very similar when they're nearby. And then the other thing is visual smoothness. So if an area was recently watered, it's going to have this darker look to it. And so we can see in a darker area in the farm, we may have, it may be similar to another one with a sensor that does have that. So those things all work conceptually. So if we put this all together, then we have a great spatial temporal view into our farm, which can yield all kinds of interesting agricultural services. I focused mainly on precision irrigation, but there's a whole lot of other work, too, I'd love to tell you about. But first, let's come back to the challenge of connectivity. So we still have this issue. We can use fewer sensors, but how could we better get that data up to the cloud? And there's a lot of different ways to do these things right now. There's a lot of different ways of moving data around. We have RFID, we have Bluetooth, we have Wi-Fi. However, there's issues with all of these things. So cellular is a great solution, but if any of you who have ever driven with your cell phone through a very rural area, you know that cell phone coverage can be very spotty in rural areas. And then there's also Wi-Fi is also wonderful, but it only stretches so far, right? I know my home Wi-Fi, if I go literally across the street to my kids' bus stop to pick them up, I'm already out of Wi-Fi range of my home network. So how could we do this? And so we're experimenting with some networking research and pioneering the idea of television white spaces. So here's the thought behind it. Typical Wi-Fi operates in roughly the 5 gigahertz range. However, if you think about television stations, they actually broadcast at a much lower frequency, and those waves stretch a lot further. So the idea is using unused television channels to send data packets and essentially create your own hotspot by doing that. Now, of course, you can't just start sending data packets over unused television channels. You have to work with the local government and make this do it properly. But this is something that we've pioneered, and it actually works quite well. And it's extremely exciting technology to me, even outside of the realm of farming. Imagine being able to connect to your home, access point from 10 miles away. Like, very, very cool stuff. And so we've stood up a pilot of this in Kenya, as well as other areas, and are doing a lot of work in this research, even outside of farming, too. So finally, putting this all together, we now have used drones, machine learning, IoT, and some cutting-edge networking research to give a real-time view into the farm and hopefully work closer towards that goal of reducing world hunger. There's a lot of other stuff we're doing with machine learning as well. We're building models to predict the best times to sow and the best times to plant crops. We're also doing a lot of work around precision pesticides. I'm really excited about that in particular, because if you can just apply pesticides where they're needed, that saves the farmer money, because they're spending less money on pesticides, which are pretty expensive. It helps with general health of everyone eating that food, and it's better for the environment as well. And then finally, we're doing some interesting stuff with low-cost weather station, meaning one of the things that's very important to measure is the wetness of leaves. And there's a sensor that does that, but it's fairly expensive. But we found that if we actually use 2 much cheaper sensors, the rain sensor and a temperature sensor, and then couple that with a machine learning model, we can actually predict leaf wetness from those 2 cheaper sensors as well. So a lot of other work in the machine learning realm. I have a whole bunch of resources on this. I did stick them all at one link right there if you'd like to access it further. And then finally, I just wanted to close by telling you about the AI for Earth program. So Microsoft has publicly committed $50 million over the next 5 years towards projects that use machine learning and artificial intelligence in the areas of agriculture, water, climate change, and biodiversity, projects like this. So I urge you, my fellow machine learning practitioners, tell your friends, and if you're doing work in this area, please apply for a grant. And together, we can build a more sustainable future. Thank you.